Hey guys, Miss Peterson here, and welcome to AP Physics 2, Lecture 6-1, all about waves in the electromagnetic spectrum. This is our first intro into our optics unit, where we're going to be exploring what a wave is, how we describe waves, and how light behaves, and how we classify light waves in the electromagnetic spectrum. So let's get into it with what is a wave. So a wave is any rhythmic oscillation, okay? Oscillation just means back and forth, okay? Back and forth. That transmits energy from one point to another, okay? So if you're in the ocean and a water wave goes by, it is not all the water that's moving from out in the ocean to back, or if you have a boat sitting on, easier to picture with a boat. Okay? If you have a boat sitting on the water as the wave goes by, the boat is just going to move up and down. The boat is not going to be moving with the wave. Rather, it is the energy that moves with the wave. And there are two general types of waves that we will classify them as. The first is a transverse wave, one like this, where you can see the oscillations are perpendicular to the direction the wave is traveling. Okay, so if some examples of transverse waves are water waves, technically those are combination waves, but they're mostly transverse. Water waves, guitar strings, okay, any stringed instrument, when you pluck it, you're going to see that transverse wave, where right now what you are hearing is a longitudinal wave. Okay, sound is an example of a longitudinal wave, where if the wave is traveling in this direction, the actual particles or medium of the wave is oscillating back and forth or parallel to that direction of motion. So the oscillations are parallel to the direction of the motion. Okay, so we're going to be talking and describing lots of waves throughout this unit and even a little bit into our modern unit. So some general vocabulary that we use is the crest, which you can think of as the top of the wave. And then the trough, which you can think of as the bottom of the wave. Okay. A node is anywhere it crosses that line in the middle, basically where the matter or material would be if there were no wave. So we call that the equilibrium line. And then from crest to crest is the wavelength, which you can also measure from node to similar node. So one trough, one crest in that, and that will give you the wavelength, which we use the symbol lowercase lambda, okay, lowercase lambda for. So the equation as it is on your equation sheet is that the wavelength of a wave equals its speed divided by its frequency. Okay, so where this is the wavelength, typically in meters, this is the velocity, typically in meters per second, and this is the frequency in units of hertz, as in the frequency of my bad physics jokes, hertz. Okay, so a hertz just means 1 per second, 1 per second. You'll also see it sometimes written then as seconds to the -1, okay, or 1 over seconds, which is just another way to represent that. But we call that the frequency. And then also back in mechanics, we do relate the frequency to the period by the equation T equals 1 over F, where T is the period, okay, or the time for 1 okay? And then frequency is the waves per second. So T is time for 1, and F is the number per second, okay? T, while it is typically in units seconds, so the seconds for one wave, frequency would be the waves per second, okay? Now, one other thing that shows up on the AP Physics 2 exam is the mathematical equations for waves. Now, this equation is actually in the mechanics section of your equation sheet. And what's kind of weird about it is it really is just a mathematical equation, okay? It says x equals a cosine of 2 pi ft, okay? So when it is in this form, the x is the position, but note, this will be whatever is on the y-axis. So in reality, this is just your y-axis. Often you'll see it in the context of the electric field or the magnetic field that's being produced by an electromagnetic wave. Okay, A is the amplitude, and it is the amplitude always. Okay, F is the frequency, and T is time, or in reality, okay, it can also be whatever is on your x-axis, okay? And that can change. Luckily, in the AP Physics 2 curriculum, they do not try to be tricky about this. It's normally a multiple choice problem where they just show you a wave and is like, hey, which of these equations matches the wave? So if, for example, they gave us a wave like this, okay, we have the time in seconds, the y is in centimeters. So we want to get the frequency of the wave. So if we have the time in seconds, I'm going to try to see about where one wave is. So one crest, trough. Okay, so it's looking like about there is one wave. And then if we look, yeah, it's a little bit off, but I'm going to go ahead and say the time for one wave is about 4 seconds, which means our frequency then is going to be 1/4, or 0.25 per second, or 0.25 hertz. Okay, so when we put this then into our equation, we have our x, our position. They have it as y on the graph, but it's still just talking about a position, so I'm fine with keeping it as x equals a, the amplitude, which is 2. It doesn't matter what units it's in because it is based on the graph. This equation is just describing the graph, and on the graph, it is 2. So 2 cosine of 2 pi times 0.25 t. Okay. Now, also note, sometimes they'll put sine there instead of cosine because, you know, it's just that little shift, that little phase shift. So you can also see this equation with sine. And you could write it like that. Another way that you might see it represented is actually calculating out that 2 pi times 0.25, which gives you 1.57. So 2 cosine of 1.57 t. Okay, cool. Okay, cool. Now, when we were studying light, we were trying to figure out what light was. Was light made of particles, okay? The ancient Greeks, one of the old theories of light was that our eyes sent something out and gathered information and then brought it back to our eyes. But then they were like, well, we can see stars, and it doesn't quite make sense for particles to be traveling out of our eyes and back to stars. So then we're like, okay, it must be a wave, like water waves or like sound waves. And we were trying to figure out what it was. And one of the main ways that we do that in physics is by testing our models and seeing which models can accurately predict the behavior of light. So we're going to go ahead and look at some demonstrations of boundary behaviors, okay, where we're looking at particles, which I want you to think of as either like little marbles. I'll also use the example of like a paintball gun. So instead of like a laser pointer, it's like a paintball gun. For transverse mechanical waves, I want you to think of water waves. And then I'll also be demonstrating it using waves on a string, depending on which behavior we're looking at. For longitudinal mechanical waves, that's going to be our sound waves. So we're going to be looking at that. And then for light, we're going to be using laser light. Okay, a laser pointer. Now, laser pointers are interesting in that lasers are collimated light. So that means all waves. Oh, I said it was waves. We already said the electromagnetic waves. Okay, and it is a wave, but maybe it has some particle nature. Is it transverse or longitudinal? We'll see. All waves have the same energy and are going in the same direction. Okay, so where example, my cell phone flashlight, okay, puts out a lot of different colors of light in all directions, okay? That's what's going on here. The laser light, you can see the light all around. You probably can't see until it hits something because light needs to reach our eyes in order for us to see it. So if we're just looking at the laser, since it's all going in that direction, we don't see it in between the path that it takes, okay? It's like collimated, all in one direction. So we're going to be looking at different boundary behaviors for each of these things and seeing which one light is most similar to. So let's go ahead and get to that. Okay, so before we get into each of these boundary behaviors, we do need to talk about what they are. So reflection, you can just think of as bouncing off. Okay, so for example, when the particle or wave hits a surface, it will bounce off. So do particles undergo reflection? What do you think? Yeah, okay. Particles can bounce off things. Of course, particles can be reflected. So, yes. Okay. What about water waves? If I send a water wave down to this wall, will it reflect and bounce back? Let's see. Okay, try one more. See if I can get a deep little wave going there for us. And yeah, we can totally see a transverse wave we can totally see a transverse wave get reflected back. Okay, a little hard with these big strings, but you get the idea. We know waves can be reflected. Now, what about sound? Okay, the sound that you are hearing right now, could that be reflected? Yes. Okay, and what do we call the reflection of a sound wave? It's an echo. Okay, an echo is just that reflection of sound waves. And we have to try to modulate whether sound is reflected or absorbed, for example, like in movie theaters, okay? If all that sound was reflecting off the walls of the theater, that'd be pretty bad. So if you look up at movie theaters, they often have these panels of a softer material on the walls to minimize that reflection. And then what about light, okay? Here we have my laser light. Can it be reflected? I have a surface of water here. Let's see. Boom. See that red dot? Hopefully you guys can see it. But yeah, that is the reflection of the laser light off the water. Okay, light can totally be reflected. Okay. Now, refraction is actually the bending of an object when it hits a boundary. And this will happen due to a change in speed. So, for example, it would go, hit the boundary, and move from whatever medium it was in to a new medium and bend. Note, this only happens if you're hitting that boundary at an angle less than about, or less than 90 degrees. So for refraction, I'll go ahead and show it to you guys with the light first because I think that's the easiest way to see it. Okay, I'm going to shine this light at a shallow angle into the water. And we can't see that path right now because, like I said, this is laser light. It's collimated. It's all in one direction. We need to give it something to reflect off of to be able to see it. So I'm going to try to do that with this borax. Okay, there you go. You guys can see that laser light. And when it goes into the water, is it going at that same angle? Okay, hopefully you guys can see that bending of the light, that refraction. Okay. But what about water waves, okay? Do water waves slow down when they enter a new medium, like going from salt water to fresh water to salt water? Have you guys seen that? Okay. Can it bend when it hits something? Yeah. In fact, if we have a lot of matter, we can even see it in waves on a string. When you go from a dense wave to a lighter wave, you can see a change in the speed of the wave. Okay, transverse waves definitely undergo refraction. Sound, okay? What about sound? Now this one's a little bit different. It took me a while to think this one out. But, question, can you hear underwater? Yeah? Okay, and what does it sound like when you hear underwater? Does it sound the same? No, it sounds all wibbly wobbly and burgly. Why? Because sound can travel through that, but when it travels from air to water, it changes its behavior. You can test this too. If you clip and get like a little air pocket over your ear, you can actually hear a sound wave that has traveled through the water and it'll sound clear because when it gets back to you, it'll refract back to the way it was. Now, what about particles, okay? If a particle was moving from one medium to a new medium and it came in at an angle, would it bend? Would it change its speed? The answer is yes, but this might be kind of hard to visualize. So I have a video to show you guys. Now, as we watch this video, I want you guys to pay attention to this truck. Specifically, I want you to watch the angle of its wheels as it enters the runaway truck ramp. This is one of those runaway truck ramps that's used when trucks' braking systems fail at the end of big hills. So let's go ahead and watch. Okay. So we see that car coming in. Good thing these people moved out of the way. And it's coming in at an angle. Did you see that front tire bend in? Okay. Let's go ahead and see if we can see that part one more time. Okay. Again, I want you to watch that front tire and see if you can see that bend in. Okay. It's coming in at that angle. Boom. Okay. That is an example of particle refraction. So, particles can totally go undergo reflection. Okay, so far, light has a lot of things in common with particles and transverse waves, and they all show these behaviors. Okay, what about absorption? Okay, so for absorption, you have to give all of your energy to something else. Okay, giving energy. So for a wave, what it looks like is the wave coming into a boundary and then gradually losing its amplitude as it goes and diminishing in intensity. You might be able to see that in the laser light in here. Okay, me mush up the borax so we can get a good view of it. Okay, but hopefully you guys can see green absorbs red. So as we go further along in the tank, okay, we're gonna have less and less red light, okay? That green is going to be absorbing the red and making it a lot less intense, okay? Light, we know, can be absorbed. Water waves, okay? Water waves. Could the wave be absorbed and have it disappear? Okay, if I have a soft boundary at one end, okay, let's see if we can get the wave to not reflect. It's still reflected a little bit, but most of that wave's energy is now getting absorbed rather than reflected. Okay, so that is an example of a water wave or transverse wave being absorbed. And we already talked about the panels and theaters that are designed to absorb your sound. But there is no situation where I throw this ball at something and the ball ceases to exist and gives the thing all of its energy, okay? No matter how many times I slam this at the table, it's not going to become part of its table. Now, you could argue this with me if we get into quantum and nuclear and wave-particle duality, but for the macro level, at the level we're at right now, just trying to figure out what light has in common with, we're going to go ahead and say particles can't really be absorbed. So they are first, nope. Okay. Now, what about diffraction and interference? I'm actually going to switch the order of these because it's a little bit clearer. Diffraction is the bending around or through. So this is something where you have a boundary, okay, and something comes through that boundary and expands after it's gone through it. So it can bend around a corner or something like that. Where interference is when the energies of two things add. So say I had these two waves moving toward each other, okay? When they pass each other, they could add and become a big wave before they continued on past each other, moving in that other direction, okay? But that's interference, that adding of it. So for this one, I can show you guys in the demonstration, but we're actually going to start with the simulation just so I make sure we can see it clearly. Okay, this is the wave interference simulation from FET at Boulder, Colorado. So with the water wave, we know that water waves can bend through openings. It will expand as it goes through. Okay, and then for sound, if I change this to a sound wave, okay, can you guys hear me right now? But there's a barrier blocking my sound wave. But it doesn't matter. Sound waves can diffract around any barriers. Okay. Then for light, okay, while we would never see light diffract around an opening like this, we can see it with more dispersed light, like this, okay? And we can also see it with super small slits, okay? This slit has to be on the same order of magnitude as the wavelength of that wave. So for light, typically instead, what we'll see, I'm just gonna turn this off real quick so I have a black to show you, this is a diffraction grating. It has a bunch of teeny, tiny little lines on it. So when I shine the laser pointer at it, okay, trying to find somewhere where you guys can see this. And something cool about the diffraction is you can also do it in all directions, okay, like here. Whoops. There we go. I'll shine that there to be my boundary. And you can also shine it in all directions and get that pattern. Now, what's cool about this is diffraction does actually depend on the wavelength. So different colors of light will diffract differently. And that's how you can get some cool effects, like, go ahead and show you. These are diffraction grating glasses, so they diffract all of those colors. Isn't that cool? Okay, cool. So that is diffraction. All types of waves can undergo diffraction, but for a particle, okay, if I'm throwing this ball at you or shooting paintballs at you through a barrier, they are never going to hit and bend around the barrier and come back to you. It's just not going to happen. Okay, particles cannot diffract. They can also not interfere with each other. Okay, interference happens when you have two waves meeting to make a bigger wave. Okay, so it's a little hard to show here, but we can get some funky waves going with all sorts of interference effect of the waves canceling and adding, or canceling and adding, and all of that. In the simulation, we can see these effects when we have a double slit. I'm going to go ahead and go to the interference part of it. Nope, that is where I want to be. Okay, so you can see where the amplitudes are adding and we're getting a brighter light, and where they're minimizing and we get those black spots. That's indeed what was happening with the diffraction grating that we were seeing. We were seeing constructive and destructive interference of the different waves making it through that grating. Okay? And if I put a screen on the back, we get what we call an interference pattern. Okay? It has to do, though, with two things being in the same place. So while it totally works for transverse waves and totally works for light, okay, what about sound? Okay, this is actually how beats were originally created in sounds. If you have two tuning forks and you hit them, okay, you can hear the sounds add and subtract from each other and create the beats that we hear in music. Okay. Now, so far, we haven't made any distinction between transverse and longitudinal mechanical waves. All we've said is that based on this type of macro evidence, light is a wave. But there's one more effect that we're going to look at, polarization. Okay? Now, polarization definitely doesn't happen for particles. And what it is a filtering of light based on the direction it is oscillating. So if you pictured this string here, and I'm sending waves, vertical waves on this string, it's oscillating up and down. If I had to dispense with vertical spacing here, that wave would make it through. But if I had a wave go in this direction, okay, going side to side, and a fence with vertical spacing, it would not go through. So we can have two polarizers at different angles that can control and block light. Let me go ahead and show you. Now, one thing that's really interesting is the light that comes from this board is actually already polarized. So using just one filter, I can let the light through or block it. Let it through, block it. Okay, where with two filters, hopefully you guys can see my face right now. I'll get it a little closer so we can see these effects. With one filter, you see that some of my face is blocked. If I add another one, a little bit more light gets blocked. But if I turn them at a 90-degree angle, then all of the light gets blocked. Okay, that is polarization. And it can happen with transverse waves because they have a direction that they're oscillating up and down or side to side or at any angle. Where for sound, that can't really happen. Okay, so because of polarization, we were able to determine that light waves can be polarized like transverse waves, but sound waves cannot. So that led to our current model of light as a transverse wave. And while it is not matter that is oscillating in the case of our waves on a string or our water waves, It is the electric and magnetic fields oscillating, but they are oscillating perpendicular to that direction of travel. And we can tell because of how it behaves. Okay, cool? Okay, cool. Now that we know light is a transverse wave, let's talk about all of the different types of light waves that they are. Okay, in our general everyday life, when we talk about light, we're typically talking about visible light, which is just a teeny tiny portion of the entire electromagnetic spectrum, which is the scale that we use to classify light. It goes from radio waves to gamma rays in order of wavelength. So radio waves have the lowest energy and the lowest frequency, and gamma rays have the highest energy and the highest frequency. Okay, where radio waves, they do have the lowest energy and the lowest frequency. They are the long and lazy ones. Okay, their wavelengths are on the order of soccer fields or houses, or can even be as long as like the universe. Okay, where we move into microwaves, which we use to heat up our food. It is true, we do use microwaves, that they are just the right frequency to wiggle water molecules and fat molecules around in our food. Okay, they have wavelengths the size of a baseball. Okay, this little dot right here has a wavelength in the same order of a microwave, and just starting into the infrared waves. Infrared waves are a little bit higher energy. Their wavelengths are on the size of our cells, and they interact with our cells, okay? We feel infrared waves as heat, okay? We, people, are a source of infrared light waves, okay? Ultraviolet light is when we start to get more energized, more energetic. Okay, they can affect your skin in negative ways by interacting with and causing a sunburn with the proteins in your skin. X-rays, even a little bit higher, and then gamma rays are the highest ones that we have. Typically, we do not make the distinction between soft X-rays and hard X-rays. We just call them X-rays. But we do need to know the general order of the electromagnetic spectrum. So I have two different mnemonics for you to choose from for memorizing the electromagnetic spectrum, from radio waves to microwaves to infrared to visible to ultraviolet to X-rays to gamma rays. Okay, the first one is rabbits mate in very unusual, expensive gardens. Okay, so rabbits mate in very unusual, expensive gardens, or my personal favorite, raging Martians invade a Venus using X-ray guns. Okay, memorize that sentence, raging Martians invade Venus using X-ray guns, and you will have memorized the electromagnetic spectrum in order from lowest energy to highest energy. Raging R, radio waves, Martians M, microwaves, invade I, infrared, Venus V, visible, ultraviolet, or using ultraviolet, X-ray, X-ray, and guns for gamma rays. Okay. Now, electromagnetic waves are special, okay, because they are created by oscillating electric and magnetic fields, okay? So this means that they don't require a medium in which to move like sound waves, okay? Sound waves need a medium. Okay? It is the actual air that allows us to communicate. The compression and expansion of the air in space that interacts with that comes from my vocal cords and travels through the air and then gets transmitted to an electrical signal through a computer, blah, 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 and then it's retransmitted through your speaker into a vibration in the air that reaches your eardrum. And thus my idea has been transmitted to your brain. Okay? And the reason they can do that is because of electromagnetism, because a changing electric field induces a magnetic field, and a change in magnetic field produces a one. So they are completely self-propagating. They don't need anything to move. Okay? And because they don't need anything to move and they don't actually have any mass, they will travel at the speed of light, which is a special speed that we call c. You can think of it as the speed of causality. And it is 3.00 times 10 to the 8th meters per second. So all electromagnetic waves travel at this speed in a vacuum. While they do travel slightly slower in air, we also use it for air. It is close enough that with our level of precision that we need for most calculations, we can treat light going through air as traveling at the speed of light. Okay. Now, because everything contains atoms, okay, and atoms have electrons, and these atoms are moving and wiggling around because they have energy. They have that constant random oscillating motion. So all objects above absolute zero, so all objects that have temperature, do emit some electromagnetic radiation, and that is called blackbody radiation. Yeah. Yep. But what about color? How do we understand color? I highly recommend you check out the Physics Girl video on what is color. It is absolutely amazing, and I will link it. But basically, say we are looking at a red apple. Okay, there is my red apple. Cool. And we'll go ahead and say it has a green leaf on it. Okay. Now, if I shine white light at it, okay, yes, I know it's yellow, but, drawing white light on my whiteboard probably won't help much. So I will just label it white light. White light is actually a mixture of all of the colors. So that means we have some red wavelengths hitting it and some orange wavelengths hitting it and some yellow wavelengths hitting it and some green wavelengths hitting it and some blue. We'll do the full rainbow. We got to go. We already committed. And some purple. Okay. The red, well, it's red. Okay. Does it absorb red? No. Okay. If it absorbed the red would never reach our eyes. Okay. And remember, everything is based on what we see. Okay. There's my eye. Okay, in order for me to see red, didn't draw this at the best angle, okay, but the red light must be reflected, okay? All of the other colors get absorbed. So a red apple reflects red, okay, and absorbs the other colors. While the green leaf would be reflecting green and sending green into my eye and absorbing all of the others. Okay. And of course, it doesn't pass through like this. This is more like a reflection. A better picture, a better model would have been to have the apple here and then the eye on the same side as the light so that you guys can see that reflection. Okay, it's not absorbing and traveling through it. It is being reflected off of it. Okay. And then when it comes to color, purple has the most energy and red has the least. And the colors are in that order of Roy G. Biv. Okay, red, orange, yellow, green, blue, indigo, violet. Okay, cool. Okay, cool. So as we go through this unit, we're going to be using a couple different models for light depending on our situation, okay? And it just depends on what is the best way to represent it. When we're talking about reflection and refraction, for example, we'll use the ray diagram, okay? where we just have a straight line representing that the light is traveling in a straight line. Where for a wave, okay, we might use a wave thing or something like this with wave fronts being shown. Okay, this is good when talking about color or wavelength or interference or diffraction. Okay, we'll need that model. Then we'll also be talking about the particle model of light. Okay, so if I had like a flashlight here, there's my flashlight, okay, it is sending out that beam of light particles. We will need this model mostly when we get to our quantum unit. Next one. Okay, that's pretty much it, but let's go ahead and do a couple example problems. So here's another wave. It has an amplitude of 4 centimeters. Okay, its wavelength, we want a crest and a trough and back up in between 9 and 15. That is 12 centimeters. We could have also measured it from crest to crest from 3 to 15, which is also 12. Okay, couple different ways we can measure that. And then if its speed is 30 meters per second, what is its period? So we're looking for speed. We know the wavelength is 12 centimeters. Since my speed's in meters per second, I'm going to go ahead and put that one in meters for that consistency. And then wavelength equals speed over frequency. That is how it is in your equation sheet. But if we want the period, okay, period is equal to 1 over the frequency. So if I put that in, then my equation becomes that the wavelength equals the velocity times the period. Hey, the distance that a wave travels equals its speed times how long it is. It's just distance equals rate times time. Okay, that's all that equation is telling you. So, So, go ahead and plug it in. We got 30 meters per second for a time of, I wrote my equation wrong. I was trying to solve for t there, so I need to reorganize that a little. T then will be equal to the wavelength divided by the velocity. So we have the wavelength is 0.12 meters divided by 30 meters per second, which gives us 0.004 seconds, or 4 milliseconds. Okay, cool. Let's try another one. Ooh, a light wave. What speed is it going? Anytime you see the word light, you can write V equals C, which equals 3.00 times 10 to the 8th meters per second. And then it has a wavelength of 0.65 meters. What is its frequency and what type of wave is it? Okay, so again, the equation on your equation sheet is wavelength equals velocity divided by frequency. So reorganizing that for frequency, we would have frequency is the speed divided by the wavelength. Okay, so plugging in our numbers, we have the high speed of a wave, 3 times 10 to the 8th meters per second divided by its wavelength is 0.65 meters, okay, which when you plug into your calculator, you get 4.6 times 10 to the 8 hertz. Okay, so let's see, we got about 0.65 meters and times 10 to the 8th hertz. So if we look at our electromagnetic spectrum, you do not need to quantitatively memorize the electromagnetic spectrum. You would always be given ranges if you needed it. But wavelength 0.65, so that's like somewhere in this range. Frequency on the order of 10 to the 8th. What do you know? It is a radio wave. Okay. Let's see, this one is slightly more challenging problem. 2 microphones are placed in front of a speaker. If the air temperature is 30 degrees, and they give us the speed of sound in air. Okay, I'll just write that down real quick. V equals 349 meters per second. What is the time delay between the 2 microphones? Okay, so we have the speed of sound in air. There's 25 meters between them. So if we're looking for the sound delay, basically we're just looking for that change in time of how long it takes the time to go that distance of 25 meters. Okay, so while this does kind of look like a wave problem, it's really just a distance over time, a speed problem. Okay, we know distance equals velocity times time. We know the speed of the sound wave. We know the time, or we know the distance. We are looking for that time. So 25 meters. If a wave was traveling at 349 meters per second, it would take 0.072 seconds to travel that distance, meaning that would be the difference between the times. Okay. And then last but not least, what is the wavelength of a radio station that broadcasts at 98.5 megahertz? 98.5 megahertz means 98.5 times 10 to the 6th hertz, mega meaning million, and it's on your equation sheet if you ever forget. And then it is a radio station, so it's probably broadcasting radio waves, which travel at the speed of light, 3 times 10 to the 8th meters per second. So wavelength is just velocity over frequency. We can plug in our numbers. And we get a answer. I'm going to write the seconds as per second so you can see how those units work out, of 3.05 meters. Yep. And that's our intro to optics. Okay, cool. Okay, cool.